For a single internal standard, what we're doing is adding an internal standard solution, a known amount of known concentration and volume of something which is not the analyte, but it acts in a similar way to the analyte. So it's a way of overcoming fluctuations. So as an example, let's say we're looking at sodium in a blood solution. We want to add something. If we're doing this by emission, there can be quite a lot of fluctuation in that, so we want to add something that's going to be similar, going to act in a similar way to sodium. So what we'll do is we'll add a known amount of lithium to both a sample solution and a standard solution. So for a standard solution, let's say we have, for a standard, 1 molar. So the final solution is 1 molar with respect to sodium and 0.5 molar with respect to lithium. And in our sample solution, we're trying to find the concentration of sodium, but we're going to add enough lithium to make that concentration 0.5 again. And what we're saying is that all we need to do is apply an equation to find this value K, and K is equal to the concentration of the internal standard divided by the concentration of the analyte, which is what we eventually want to find, and multiplied by the signal for the analyte divided by the signal for the internal standard. So in this case, we'll measure both solutions. Know the concentrations. We got to know the signal of the analyte for the standard. So let's say in this case that was 1420 arbitrary units, and the signal for the lithium, which is the internal standard, was 720. And then we'll do the same for the sample solution. Sample for sodium, the analyte in this is 1570. And the signal for the lithium, the internal standard, is 842. And what we can do is plug in these values. Since we know concentrations and signals for the standard, we can plug those into the equation and find K. And then that value of K is going to be the same for the sample. So then we just rearrange this equation for concentration of the analyte, and plug in our value of K and our other values for concentration and signal for the sample. So let's find K first. So we find K from the standard solution. So K equals 0.1 over 1 is the concentrations. The concentration of the internal standard divided by the concentration of the analyte, and the signal for the sodium, the analyte, over the internal standard. And that gives us a value of K of 0.91. Okay, now we can plug this back into the equation. We'll rearrange that equation for Ca, and we'll get that it's equal to the concentration of the internal standard over the value of K that we just calculated, multiplied by the signal for the analyte divided by the signal for the internal standard. So these are different signals now. These are the signals for the sample solution. So concentration of the analyte equals concentration of the internal standard, which we kept at 0.5. The value of K, which we calculated as 0.91. Then the signals for the sample solution were 1570 divided by 842, and that gives you a concentration of 1.02 molar. Now this is the concentration in the total solution, so analyte plus internal standard. So you may need to convert to get the concentration of the analyte in just the sample.